Good afternoon and welcome. I am Pilar Suarez and I am the Teacher Fellowship Coordinator in the Inter-American Teacher Education Network, or ITEN for short, an initiative of the Organization of American States. I'm pleased to welcome you all to this webinar, one of our series of webinars, COVID-19, Teaching STEM in Quarantine. Before continuing, I will briefly introduce you to ITEN for those who are not familiar with us. The purpose of ITEN is to improve the quality and equity of education through teacher education in the Americas. To do so, we offer funds and activities for educational leaders with the intent to resolve problems of policy and practice related to STEM teacher education, in which STEM refers to science, technology, engineering, and mathematics. To learn more about us and how to get involved, visit our website. The link will be shared at the end of this presentation. Given by ITEN project teams, participants, teacher fellows, and other network supporters, this series of webinar objective is to support the efforts of teachers during the time of quarantine. To join future webinars, again, please visit our webpage, will be shared at the end of this presentation. This evening, we are pleased to have a presentation by Professor Marcelo Caplan from Columbia College in Chicago in the United States. Tonight's presentation will be approximately 45 minutes. During the presentation, you are welcome to ask questions using the Q&A tool. At the end of the presentation, he will answer a select number of questions. This webinar will be recorded, and the recording as well of the slides will be linked to the ITEN COVID-19 webpage in approximately 24 hours. You will receive a notice that the recording is uploaded. The message may also serve as evidence of your attendance in a place of certificate. You should need to show it to your administrators. Additionally, we would like to express our gratitude to the questionnaire portal of the American, which is providing support to transmit the presentation live via their Facebook page, and especially to our donor, the U.S. mission of the Organization of American States. At the conclusion of the webinar, please do not forget to complete the brief survey that will be helpful in determining future webinars. Thank you very much. And now I will pass the presentation over to Marcelo Caplan. Marcelo, welcome again.
Hi, good evening, everybody. Good afternoon, good morning, whenever you are. My name is Marcelo Caplan. I am a professor at Columbia College, Chicago. It's a media and art school, but we have a department of the science and math department in which we promote all the time how to communicate STEM in the communities. And this is one of the best things that I am doing in my life, that is sharing with you guys things that you can maybe bring to your communities if you believe that has value. I am doing this kind of activities for more than 2 weeks, meaning I am a couple of 20 years promoting STEM in the communities. And now I want to share with you a couple of ideas about computational thinking and how we can implement it in using microcontrollers in the time of the COVID. Okay, we know that we are living different, very, and the word very will not express the difficulties that we have now in communicate with our students, in communicate with the parents of our students, to be able to obtain materials so we can work with our students. So this presentation will try to facilitate a way in which we, despite that we are at home and despite that our students are still recluded at home, they will be able to develop programs and test programs and use their computational thinking to solve problems. So let's move on and start. Mouse here. Oops.
Marcelo, for some reason, I don't know why, your screen is not showing as enlarged
Uh,
on.
I believe that Pilar still is sharing my screen. Sharing?
Not sure. I don't believe
No,
so.
I'm not.
So you need to pin my screen maybe?
Perhaps so.
Because the last time was okay.
Okay, it looks like it's working now. Thank you.
Okay, excellent. So where I was here, let's come back to where I am. Let's move here. And first, we want to have a brief discussion about what is computational thinking that is not only relevant for the use of computers or for computer science. Computational thinking is a way of thinking. It's a way that allowed us to solve problem in a methodological way, in the way that we can take any kind of problem and make it simple following certain strategies, okay? And when we talk about computational thinking, we can see that we are dealing about take a big problem and decompose this in simple problems. From there, I will try to find a pattern. Maybe these simple problems are following any kind of pattern that I can be able to discern. And if I have these patterns and I can discern these patterns, I will be able to abstract this pattern. What does it mean in making abstraction? I don't need to solve a problem specific for a specific situation. I can make a generic problem that will solve the same situation that follow different patterns. And then we will have the capability to create a set of instructions that will allow me to solve this problem. Okay, this is what people call an algorithm. But all the stuff that I mentioned here are activities that we are doing in our regular life without any kind of problem. Okay, so every time that we wake up in the morning, okay, we call it the wake up time, and we divide it in different processes that are small, and each one has different questions that I need to answer, and each one has different patterns that I can identify. And for each one of these situations, I can generate my own algorithm. And if you think about this stuff in this way, you will be able to see that any activity that we are doing, you can divide it in this simple process of decomposition on simple problems. You have recognition of patterns, pattern recognition of things that are happening in each processes, and you will be able to make a general model of these processes, so you don't need to investigate each one individually. So use the model to solve problems that are repeating itself. And after this, you will apply all this knowledge sequentially to follow to create your own algorithm, how you make your coffee, or how you take the shower in the morning, or how you buy shoes. And then what you want to do is a process that is not in this transparency, in which you will evaluate if the result of this algorithm is solving your problem or not. And if it's not, you come back from the beginning and you're doing the process of engineering design to the computational thinking process. So in this way, you can see that when we talk about computational thinking and we talk about engineering design and we talk about the scientific method, we are not talking about different things that are not connected. All these methods, all these ways of thinking are different ways to solve different kind of problems. And everyone is intertwined, and you cannot solve problems if you don't know the scientific basis. That's the reason that we want the kids to know the scientific method, but if they know an engineering design process, they will not be able to generate a solution. But if I don't know the computational thinking, will be very difficult for them to follow and create a model that will solve the problem that they want. So in this way, we can see that all these processes are very, very connected one to each other. Generally, the top of computational thinking is linked to robotic. And we can read all this stuff that is very important, but the reason that everything that we do in computational thinking is linked to robotic, it's very simple. People love robotics. You say the word robotics and everybody say, yes, I will. You say science, you say engineering, it's like school, boring, or whatever you want to put. You say adults, that they see a little robotico, they will stop and see how the robotico is moving. But if you have a machine that is doing their job and is doing exactly like the robot is doing, no one pay attention. So this issue of robotics, and you call it a robot, is creating a lot of attention, and we as educators, we will take it, it's in our benefit to take advantage of this stuff and use it, this intrinsic motivation that the robot generate to improve all, or introduce all the capabilities and abilities in science, technology, engineering, and mathematics together in the way that we are doing, because robotics is an umbrella that allowed us to do this stuff. If you pay attention, if I talk to a student to learn about the lever of the fulcrum on the lever of on the lever, it's boring, blah blah blah. But if you do an robotic arm that is exactly the same, oh my gosh, I am doing a robotic arm, it's so cool. But the lever and lifting something with a lever, boring. So, like I say here in the point number 3, we need to put robotics in the academic context. So people love robotics, okay, let's use robotics to do this stuff. And that's the reason why robotics is so linked with computational thinking, because also in robotics, I have a system that need to understand a problem, they need to find the patterns and generate an algorithm that will solve this problem. Robotics is a very, very good example for this to do. And according to the MIT, we know that robotic and learning is awesome. So if the MIT, they are running the program Scratch for more than 10 years, and they have a lot of research about this stuff, I agree with them. So now I want to share with you a little experience that I have using computational thinking and robotics in this integration through working with teens in my lab. Okay, these teens are not my college students. They are teens from the Chicago public schools, and they are participate in the after-school program that's called Junior Research Scientists, in which I am introducing them to alternative energies. And here we have the problem that what we want is to learn about solar energy, and we want to explore how is the best way I can collect solar energy to power my own devices. And when they were learning about the topics, they start to explore by themselves. They found the problem. They need to learn about what is the relation between the intensity of the light and the distance and the energy they can convert. What is the relation between the angle, the incident angle of the light to the solar panel, etc., etc. And after this, they need to learn about the properties of the photovoltaic array that they are building. What is the current of short circuit, what is the voltage of open circuit, what is the maximum power, and all this stuff is motivated by the fact that I need to charge my battery as fast as possible using solar energy. You can see in this picture here, they are building their own solar panel, so they will have at the end their own solar panel. But the point is, we learned that the angle need to be perpendicular. The light need to hit, if this is my panel, the light need to hit perpendicular to the panel to have the maximum conversion. And to do this stuff, I cannot be sitting there and changing the panel. So they think to design what they call a solar tracker. Here we can see one of my students building a solar tracker. It's a tripod with 2 motors, and these 2 motors will move the plane of the solar panel in multiple directions to be sure that the panel is following the sun all the time. Okay, this is more or less how the panel is mounted and on the solar tracker. And you can see here the 2 motors, that one is moving the motors in the plane XY. If this is the plane XY, another one will meet the YZ plane. So we have control about the azimuth and the position of the solar panel. And this will be made by 2 step motors, and the tripod was made in the 3D printer. So this is more or less, so you have an idea. Again, we use all the time free software to do this stuff. Autodesk 123 Design is free. and my students need to figure it out how to use it and how to do this stuff. Now we have the solar panel, but how the solar panel know when is the maximum of the light? We have here a sensor. Someone will collect information when the light is the maximum. We will have certain information that will give us the information needed to say, oh, I am in the right place. If not, I will need to move and adapt. Okay, and we have the input of the system will be the value of the photoresistance that we have that will change with the intensity of the light, and the two motors that we said before, we will be able to move the panel to ensure that the reading of the photoresistance will be all the time as big as possible. Okay, now I can do it by myself and sit there all the time, but it's not the goal. So for this stuff, we decide to use a microcontroller. The microcontroller is a device in which they have the capability to sense inputs and activate outputs in the real world. And the relation between the inputs and the outputs will be what I want through the code that I will write into the system. We use for this program specifically the Pro Trinket that is from Adafruit. The Pro Trinket is only, I choose this one because it's cheaper than, at this moment, was cheaper than the Arduino, and it was smaller, and they have more or less the capabilities that we need to make this project. So there's no reason to use a big tool if when small tool, I can have the same results. To train my students to use this microcontroller, we built a training board. You can see here the microcontroller, and we have LEDs that serve as outputs, and we have here a switch that could serve as an input, and we have here a motor that will be an output, and we have here a range sensor that will serve as an input. Why we have this stuff in this way? Because I want to have a board that the students don't need to be all the time testing if they did it right or wrong. I want them to learn how to process their thoughts through the microcontroller and ensuring that the responses will be valid according to what the board is showing them. And we build the stuff. This was part of a large presentation I did. There is the way that we connected to the microcontroller, to the board, only for information. The point is that when I have the board, I will be able to let my students to train, to practice and train. Now, to write the code, we have here another problem. Another problem is that generally when you go to Arduino, for example, the code, it's a similar kind of code like C++. The point is that there is too much possibilities of error writing the code, and this frustrates the kids at the beginning. After this, when they are more specialists, they will be more able to see their own errors and they correct it in the top. But I prefer to use a graphic interface that in this case we call is an interface called ArduBlock. This is providing the capability to make this algorithm in the way of a flow chart with the same logic question that you are doing in the flow chart, and will allow my students to review their program visually without trying to, okay, I read code, I need to translate to my brain what the code is doing. In a graphical input, I can see if my code is doing what's supposed to do. And here we have all the logic, the same logic. We have loop, we have question, if, else, we have activities that say set something, give a value to one of the ports, read the value of the port, and let's mathematical operation. There is a lot of different activities that we can do with this, with the ArduBlock that does not limit the capability of the students to write their own code. And here we have still, when I am drawing this stuff, I am drawing a graphic. Now we need to convert this graphic in something that the microcontroller will understand. The microcontroller understands what they call the binary code, ones and zeros. So we have here two processes. We call it compilation. Compilation is to move from one language to another language. we go from the graphic language here. The first compilation is that the Arduino block will convert it into code. This code that the interface or IDE of the Arduino will understand. And after this, we will compile it again and we will convert it in a language that the Arduino or let me show you here. The Arduino here will be able to understand. The Arduino is connected here to the USB to the computer, and we have here the board that we discussed before, so we can connect from the Arduino to the board, and I can be able to test my programs in real life. Let's come back here. Here we have a different version of this is the Tinkercad Pro, only for you to see. And here's the board that is being used. Okay, we make a little program and we say that the program needs to change the LEDs working. That's only for you to say that, for you to see that it's operational. And the important thing is that my students will be able to practice with this stuff. Okay, after this, we make also a little robotico. We have here 2 motors that are moving the robot in any direction. We have here a range sensor, and the students, now that they know how to write the computational thinking processes for the robot to solve a maze, they can write the code and they can find patterns and they can do everything that they need to make this robot to move. Let's go back to the screen here so you can see the robot. This is the little robot that we talk about. We have here motors, 2 motors that are step motors. We have a range sensor. And with this stuff, my students that practicing before in the board that we designed, they will be able now to start to implement their computational thinking to make this robot to do a specific task. This is supposed to be a video that doesn't work here. But my point was, okay, I train my students, but it's not enough. I want my students to be able to communicate it to other students around the world or around the country or around the whatever we can. And you can see my students here, they are presenting these computational thinking skills or introducing them to kids in the Museum of Science and Industry here in Chicago, but we were to different schools and we are promoting our teens to be able to communicate what they are learning because, hey, if we are investing in you, you need to be able to share with someone else. And this is my mantra. Okay, but now we talk a lot, more or less about how I can take from an idea of a problem, how we can write a program, or how we can activate a microcontroller to solve this stuff, or how we did it. But now I want you guys to do it with me. Okay, if this were a workshop of 3 hours, we will stop here and I will ask you to do a lot of things now. But because it's a webinar, I want to introduce you and we will start to work like together, okay? And the point is that we say that now we are in quarantine, we don't have the capability to bring all these materials to the students, or the students could not come to the school to use all these materials. So what we can do? We are using now a simulation. And the simulation that we are using called Tinkercad.com. So let's go to the simulation and let's work together. Okay, this is my Google page. I go to Tinkercad.com, boom. And I know sometimes if the students don't have connectivity, we have a problem. Okay, the point is that there is a couple of things that if I want to do remote learning, I need to have it. If we want to do a virtual learning, I need to provide, or I need to be sure that my student has access to certain kind of connectivity, so they will be able to use all these resources. Okay, now we have a Tinkercad. I will log off from here so you can see how Tinkercads look when you don't have an account. Okay, that's the beautiful of this stuff. By the way, Tinkercad is free, okay? And you as a user, you need to join if you want to use this stuff. Because I joined, I will sign in. He will ask me for the way that I will sign in with Google. They will ask me which Google account I am using in this tab. This is my Google account. And now we will be ready to work in Tinkercad. So Tinkercad is an excellent program to do designs in 3D. That was Autodesk. Remember, we did it before to make the legs of the solar tracker. But here we will use the circuits. Okay, circuits. You can see that I did a lot of circuits, and I will do a new one for you guys, so you will see how the stuff came when you are starting from scratch. Not the program scratch, okay, sorry, from the beginning. You have here different kind of components. We are using the basic components. And for the basic components, I will choose 2 components. We have the Arduino, okay? This will be our microcontroller. It's coming. Using the letter R, I will turn this stuff so it will look nice in our board. You can see the stuff. And we can bring also the breadboard, protoboard, etc., that there have too many names, but it's the one that I can use to connect the real things, okay? So now what we need to do is to start to learn how we can use this simulation in my own benefit. So the first thing is we understand that when we are using devices, the devices could be on or off, okay? So we can decide, and there is a lot of, at least another hour to explain how I move from a multi-meaning language to a one-meaning language. For example, I have money has multi-meaning because I really don't know what does it mean. I have money. Could be $1, could be $1 million. But if I want to go to from a multi-meaning language to a one-meaning language, I have more than $10. So this proposition could be or true or false. Okay, there's no more meaning. So when we go to computational thinking, the first thing that we want to do is to go from the multi-meaning language to one meaning language. We know that every proposition could have only 2 values, true or false. And from there, we can continue moving. So let's start to figure it out, something that represents on or off. Could be a lamp, okay? And in this case, we are using an LED, okay? I will not go to the electricity of the LED. For this moment, you will believe me that I am doing the right thing. I will have a resistor connected in series to the LED, and I will need to connect the ground. You can see how easy I am doing this stuff. And why is so easy? Because I have experience. If you want to have the same experience, what do you need to do? You need to sit down and do it. So I connect the ground here, and I will put only the 5 volt. Let's put the like a battery in the top connector, only so we have ready for the rest of the activities. Okay. Now you can see that the LED has not connected to nothing. Well, let's put this stuff here. The LED is not connected to nothing. If I remember, this is not a real life stuff. This is simulation. So if I will run the simulation, the LED will not do absolutely nothing. So if I will connect the LED to the battery, for example, okay, for the moment it's off. If I start the simulation, the LED turn on, okay, because I am giving energy to the LED. So in this moment, we just have a board that has a battery of 5 volt that I can use it, and I can build whatever I want here, and I can test it with my simulator. My simulator has also a voltmeter that I can use it to measure voltage. And let's put it, the positive is here, only here, and the negative, let's go to the bottom here. And if I can change the color of the wire. Let's put black for this one, and let's put it red for this one, because red generates positive and black is negative, And now if I go and run the simulation, I see that the voltage of the battery is 5 volts. Okay, that's what the simulation is doing. So let's stop it. I hope that for the moment it's clear, but I didn't do nothing strange. I am not using my microcontroller. I am using the controller as a battery. But I want now to turn on and turn off the LED because this is what I want to do. So what happened here, the microcontroller has inputs and outputs, part of digital and parts are analog, okay? Analog is another story for another webinar. Let's use the digital. Digital are the ones could have only 2 values, or 1 or 0, on, off, open, close. So I will choose and each one of these guys receive the name of pin. I will take the pin number 7 because I like the number 7. If someone has a problem with it, you can choose another number when you will do it at home. Okay, I will connect the pin number 7 to my LED and I will run the simulation and the LED will be still off because although I connected to the microcontroller, I didn't tell to the microcontroller what to do. So if I want to tell the microcontroller what to do, I need to introduce a code. In my time, we call it a program. Now it's fancy to say code. So let's call it code. So let's input the code here and let's delete the code that was before. And I can see here different kind of activities I can do with the pins on the output side. So if I want to turn my LED, I will take this order that called set pin, give a value to the pin. I connect it to the pin number 7. So let's put the number 7 here. Now I want to make it high. High meaning on. I am giving power to the LED. So if I am running this simulation here, now you can see that the LED is on because the Arduino is doing what I just told them. Please turn the pin number 7 on, period, nothing more. Now let's do something else. Let's make it only turn on and turn off. So let's stop the simulation and let's go now and only make the device to wait 1 second. And let's now add another one, pin number 7. And now I will turn the pin number 7 off, low, okay? And I will wait another second so we can see what happened. You can imagine now that what the program is doing or what the Arduino will do now will turn the pin number 7 on. I will wait 1 second. I will turn it off and I will wait 1 second. So what we see will be the pin, the LED blinking if I did everything right. Let's see. Oh my gosh, everything is doing like I promised. And this is what's supposed to be because we are following what you call it, the computational thinking. I want the stuff to make it blink, how I will solve the problem, turn it on, wait, turn it off, wait. And that's it, that's all my problem. And now I want to be able to test it in my board, okay? So what I can do now, I can go to the code here. Okay, go here, but I will stop the simulation. And I can see that he prepared also the code that the Arduino could understand, okay? So I will open the IDE of the Arduino. The IDE is the interface that can use to program the Arduino. It's opening. Okay, it's in my other screen, I will bring in a second so you can see when I finish opening. Okay, I apologize, this takes a little bit time. I am using a computer that is managing 3 programs, 2 screens, the mixing of the images, and it's 5 o'clock, it's tired. Okay, so I will now, this is the Arduino code, I will highlight it, control copy, I will go to the Arduino interface, I will control paste, control B, and now I have the guy have my first compilation from the drawing to the text. And now Arduino will go from the text to the language of the machine that my microcontroller connecting the other side will work. So I will go and compile this stuff and upload. What does it mean upload? Moving from my computer here to the microcontroller, because the microcontroller is the important. It's not my computer. That's the reason we call it upload. When you are bringing music from the system, you are downloading because your terminal is not important. The other one is the important. So let's upload this stuff. Okay, it's working. It's trying to do the stuff. I am watching until the stuff will end. Still working. Okay, success. He did it. And I will go now and show you my beautiful red LED blinking. And you can see that the red LED is connected to the pin number 7. If I, by mistake, will put this stuff in another pin, let's say pin number 9, the LED will not blinking because what we want is to reproduce what we have in the simulation. Let's put it to the pin number 7, and we have the LED blinking. Okay, so for the moment, we are doing this stuff. And if I have one LED, if I can control one LED, I can control whatever I want because it's the same. I can turn off and turn on, turn on and turn off whatever I want. So to make decisions, I need to have input from the real world. So we come back now to our simulation. And let's close the code here for a sec. I am the wrong stuff here. Let's close the code for a second. And let's take the multimeter for a second. And I need to have an input. And an input could be something that I can give to the system. To make an input, I will use a slide switch. Okay. Slide switch has 3 legs. Let's connect one leg to the positive. And let's connect another leg through a resistor to the negative. And now let's measure, let's delete this wire here, and let's measure the voltage in the slide of the device. Let's go to our simulation, and we can see when the slide is 1 high, we have 5 volt. If I move the slide to the other side, we have 0 volt. 5 volt, 0 volt. 5 volt, 0 volt. Meaning I cannot tell to the microcontroller do something or check something. I need to give an input, and to the input, I need to give the information that I want, 0 or 1. Let's connect this stuff. So we put it in the input number 4, I believe. So let's put the wire from here to the input number 4. And let's, oh, I am still in the simulation, sorry. Let's stop the simulation. Let's go to the input number 4 and let's connect it to the switch. So now we can write the code where we have, according to the switch, I can decide what to do. So let's go to the code and let's delete this stuff. And let's put something that will ask if something happened, and we need to put the condition. And the condition comes from here, mathematics, and you can see here we have a condition that fits this kind of setting. I apologize, I'm getting a little bit fast, but it's only to give you the idea that we can make processes in which we have questions. Now, the input, the variable, I need to create a variable here, or we can use the input straightforward. Let's see, we can have the read. I need to give a look, this stuff fit here perfectly. We can read the pin number, and I connect it in pin number 4, and the pin could be equal to 2 possible values. Could be a high or low. If the pin is high, I would like the system to do what? Let's turn on the LED. So let's put pin 7, and we remind high. If the switch is off, I want to take the same pin, and there will be pin 7, is where the LED is connected, and let's make it low. And now, let's see if the stuff works. So let's go to our let's close this tab here. Let's go to our simulation. Okay, and now we have, when the pin is high, the LED is on. If I move the switch, the pin 4 is low and the LED is off. Now, if I can do this stuff, I can do now whatever I want with questions. Okay, so now I am able to do a lot of different problems because I can have inputs that are for the moment digital inputs, and I have digital outputs. Could I activate motors? Could I activate sound? Could I do a lot of different things? Could I see if the lights are on, off? Everything that has 2 positions or 2 states, I can use it as an input. Is the door of my room open? If the door is open, turn off the light. If the door is closed, turn on the light. It's the system we just did here. Okay, so let's see the code. That's the code of this tab. So let's copy the code. Control copy. Let's go to the ID of the Arduino and let's paste it. Control D. And let's upload it. Chan, chan, chan. It's taking a second. Okay, we did it. Now you can see, let's go to my board here. The LED is off. I connect it here. If I turn the switch, the LED is on now. I turn off the switch. So I can control it. It's very, very simple, no? We have a switch that is turning on and off LED using an Arduino. But if I can do this stuff, I can do other multiple things. So let's come back here and let's come back to our presentation. And that's what I have for my time now. What happened here? Oh, it's coming. Thank you very much for your attention today, guys. This is my contact if you want to email me or be in touch. And we have still like 17 minutes for questions. So I will pass it to Pilar to manage the questions, please.
Hi, Marcelo. Patricia here.
Patricia.
Hi. I will help you moderate the questions. First of all, thank you so much. That was such an incredible presentation. Thank you so much, Marcelo.
My pleasure.
Since we don't have too many people, I am wondering if we can allow folks to actually ask questions.
I approve. I approve the motion. Everybody want to open the microphone and ask questions? I have no problem.
Yeah, Marcelo, I gave you host access. Do you by any chance know how to give me back host access?
Yay. Give me 1 second and I will give you.
Thank you so much.
Patricia, and I will go more and I will make a host. Now you're the host.
Perfect, thank you. All right, guys, if anybody has any questions, you can just say here on the Q&A, and I will, and if you're able to unmute yourself, feel free to go ahead and unmute yourself and ask your question. I think you're able to talk, or you can also raise your hand. I think there's the possibility of raising your hand, and I can unmute you.
You can, I think that in this short group, we can unmute all and that's it. I don't know if
yeah, that's true.
I don't see the button here, but maybe you are the host now, so yeah.
Yeah, let's see. How do I unmute everybody?
So everybody, you can speak.
All right, does anybody have any questions or want to say anything?
You're too quiet.
I know.
Oh, everybody's,
We could share some questions that we have in the other group, Marcelo, like the worries about the teachers, what happened in different contexts, if what have to do some teachers who wants to explore this way to work with the students. You know, probably it could be a great with them about the reflection in the other teachers group.
The idea, the fundamental idea is that we are living now in a very difficult moment in which we don't have access, or the students don't have access to this kind of material. And I don't know if you are aware, but there is what they call the bubble classrooms, in which privileged kids, I call it privileged because they have the access to these classrooms, are learning in a group of 3 or 4 with a private tutor, and they are continue learning in the time of the pandemic, when our kids in the non-privileged groups are not having the capability to access to this kind of education. And what we are doing is still fortalecing the big gap between the kids that have the access to this learning and the kids that don't. So one of my intention with this presentation is to promote you and give you a couple of tools so you can interact with your students. I know that many of them do have connectivity. This I cannot solve. For the people that has connectivity and have the capability to have access to a normal internet, they can continue learning and they can continue develop your computational thinking and their own skills despite the pandemic. And the difference between where I now and what we will be at the end of the pandemic time will not be so big. I am really concerned about what happened when normality that we call, whatever we call it normality in the past, will happen, and our kids will be at least 1 year behind the other rest, so the rest of the students. And this is really scaring me. That's the reason that I almost forced Pilar to put me in this webinar today, so I can share with you tools that I believe that you can use in your countries or in your communities. So I am ready to work with you guys, and I need to hear what you think about this stuff, because I can talk forever, but it's not the goal of the webinar now.
Exactly. Well, everyone should have the ability to unmute yourself and then go ahead and ask a question. So feel free to unmute yourself and go ahead. And I don't know if you're able to turn on video as well, but if you can, go ahead and do so. And feel free to ask questions. Or if you don't want to ask, you can always type it in the Q&A box and we'll read it out loud. Looks like this is a shy group, Marcelo.
Okay, no problem. At least I want people to say, did this presentation promote something on you guys? You think that this presentation was worthy? I need to know this stuff. At least someone write in the chat, oh, I think that I spent 1 hour and really it's useless to me. Oh, that's a good presentation. I can try to use it with my students. Something that give us a feedback that at least we did something.
Okay, Gina wrote, it was worth my time.
Thank you very much, Gina.
All right, anybody else?
Are you planning to use this stuff with your teens, with your students? That's a nice question that I am asking you. If you want to answer, okay, by sure.
We have another comment. Yes, very helpful to help promote learning at home. L. Edwards wrote.
Thank you, Edward.
Raul Castillo wrote, interesting webinar. Thank you.
Mm-hmm.
We have a question from Oh, okay. Brian Robertson wrote that he missed a substantive part of the presentation. Is there a video? Brian, absolutely. There will be a recording of this webinar, as well as all the other webinars that I-10 has hosted in the past, and it will be posted on our website. And we will write the website on the screen here pretty soon. So you'll be able to check within 24 hours, you should be able to check it and find the recording. So no worries.
Okay, in the middle time that people are thinking if they have a question, I want to let you know that to promote STEM in the community, it's fundamental for the development of the Americas, not only for our kids, it's for all the continent as one. Remember that we are in the midst of the fourth industrial revolution, where the skills that the kids, the students need to have are being totally different to the ones that we used to believe that the kids need. So I strongly recommend you guys to think about these webinars and how to promote STEM in the communities as I will call it like close to the human right. Our kids need to have this knowledge to be successful citizens of the 21st century in the fourth industrial revolution. If not, all our continent will be all the time behind the people that are investing in the education of their people. That is my 2 grains of salt.
That's very true. Very, very true, Marcelo. All right, folks, I posted the link to our website where you can access Marcelo's video within 24 hours. So please make sure to copy that from the chat. Do we have any more questions, any comments? Would anybody like to make a comment to Marcelo?
Well, we want to say thank you, Marcelo, and we really appreciate all your collaboration with us, with the I-10, and I think some teachers will apply all this information that you share with us. Thank you so much.
I am curious. No one asked me if there is another platform that we can use that is not Tinkercad. Because Tinkercad is one. Okay, there is another one that's called Microbead that is part of Microsoft stuff. So let me show you. Let's go here. I am here again in my screen. Let's go out from here and let's close this tab. We don't need it. And let's go to, everybody is looking at my screen now, I hope. And we go to make code microbead.org. And this is another platform that you can use to make codes and programs using another platform that's called Microbead, and they have also a little card. I don't know if you were aware of this stuff. The card has also motors, has a lot of good stuff that you can do. This program, for example, was designed for a situation in Argentina that could not be more than 5 people in a store. So every time that a person is going into the store, I will push the button A, and the count is increasing. And we have here a lever or a barrier that is low now. We have 2, 3, 4, 5, up. 5 is the maximum. After this, the only way that a person could go into the store is if I have at least one person going up, going down, going out of the store. And this is another platform that we can use. This stuff is in Spanish, but you can come here and change the language in some place. We can change to English here. And now you have Microbead in English. The same program, okay? So this is another platform, and the card that comes here is very, very accessible. I don't use the word cheap because I don't know what chips mean, but it's accessible. Accessible is that people with lower resources could be yes, we can use everything to solve when you call problem related to art. What does it mean? Okay, problems are problems. Okay, and if you want to build something or you want to make lights change, work in different patterns, we can. The point of art is very, very open. Okay, but every one of these two platforms could be connected to external devices, and we can make things interesting. You can make this stuff to. Well, I think that the default in this platform, when you buy it, is a heart that is pumping. Okay, so art, it's a little bit. I like it. I like the question, and you need to define what you want to do, and you will be able to do it. So I believe that now we are running out of time. So I will come back to Patricia. If there's something else that people will know, I appreciate it. If not, you are ready to close.
Thank you so much, Marcelo. I don't see any more questions. So again, we just would like to reiterate how grateful we are to you for sharing your time and your knowledge and resources with us and the whole community. We're really grateful. Thank you so much. And thanks to everyone who took the time and joined us today. And once again, you should be able to access the video for this presentation within 24 hours. And as Pilar said, you will get an email also within 24 hours with a link to the video and the presentation, and you can also use that as your proof of attendance in case you need to present that to anyone. There you go. Thank you so much for putting it up there, Marcelo. I have shared the link in the chat as well. Hopefully everyone got a chance to see. I'm gonna reshare it again, just in case. Make sure you copy it if you're interested. Just a second. All right, well, thank you guys very much and have a great evening.
Everybody, enjoy your evening.
Thank you so much. Thank you again, Marcelo.
Bye-bye. Have a nice evening, everybody.